So what do you think the 75 is? The initial height, so h sub 0. And what do you think this initial velocity is going to go in for? Okay, so we're given then a y equation of negative 16 t squared plus 76t plus 75. Now, we actually graphed these before without parametric mode. We did y equals negative 16x squared plus 76x plus 75. So far we're not doing anything that's unique to parametric equations. However, what a parametric equation will allow me to do is simulate the motion and make it stop at these heights. Whereas when it's in function mode, it just keeps on graphing, okay? So let's take a look. Let's put these in. And so we're going to make our x be t, because this is going straight up. In a minute when there's an angle, we're going to use some different parametric equations. And our y is going to be this parametric equation that I got from the information in the problem. Okay. So what I do to simulate the motion, first of all, we got it when we're picking our window, t is time, it's not going to show up. So if I wanted to graph the first second, I would do 0 to 1. It's going to show me 0 to 1 second what the flare is doing. And then if I wanted to do 2, I'm going to do 0 to 2 in a second and show you that. When we're picking our window, what we have to remember is we're 75 feet above the water, and then what's going from there? Is it going up or down at first? Up. Okay, and so when we do our y max, well, first of all, if x is t here, I'm going to just do 0 to 10 seconds. Okay. But for y, maybe I want to see a little below the x-axis, but I'm going to start by making that 100. Maybe I'll make it 150 and see if that's enough room. Okay. So there, did you see the first second? So what's the flare doing? It's on its way up. Okay. If I wanted to see the first two, well, actually, let's do this. Give the height. I'm going to trace, and because I set it this way, it's going to allow me to show 1 second. So 1 second, what is the height? 135. So let's write that down. Okay. Looks like I'm going to need a little bit more space on the top. So when I set my window the next time, I'm going to do 0 to 2 seconds. And I'm also going to increase my y max. I'll do 250 just to be safe. Okay. So is the flare still on its way up? Looks like it. Getting close to maybe the top. Let's trace that. And at 2 seconds, it's 163 feet. And what's happened at 4 seconds? It's on its way down. But do you see how that's kind of nice, how we can actually stop t, whereas we couldn't do that in function mode? And then let's do 5 seconds. Okay, and so if I was simulating, I would really, if I was doing all of these, I would really have 1, 2, 3, 4 pictures. But let's just graph the last one. So this was 250. this is not a picture of the flare's motion, okay? This is just what the height is doing versus time. In a second, I'm going to show you how, when you are given an angle, how you can actually simulate the distance something goes. Okay. So sometimes, or most times, that we're going to use parametric equations for motion, because this is something that isn't new. We did this in algebra, not in parametric mode, but with y equals. We're going to involve an angle. And so you're going to see in the next problem, Kevin hits a baseball, and the baseball is leaving at a certain angle. And so we're going to just copy down our equations from this, but the x parametric equation, we would take the initial velocity times the cosine of the angle, and don't forget times t. And so what we're trying to figure out is, how is the ball, in this case, moving horizontally? That's going to figure out that part for us. And then we've already talked about vertically, we need this negative 16 in here, but we only want then the part of the angle that's going vertical. So we're going to involve a sine. So we're going to write negative 16t squared plus initial velocity times the sine of theta times t plus the initial height. Okay, so what I'm going to show you is how you can graph this, and then I'm going to even show you how you can put the wall on there. Kind of cool. So we can see an actual picture of what's going on. Alright, so Kevin hits the baseball 3 feet above the ground. What's that? Yep. With an initial velocity of 150 feet per second and an angle of 18 degrees with the horizontal. Will the ball clear a 20-foot wall 400 feet away? Okay, so that's what you think. Let's find out. Alright. So let's use our parametric equations. We're going to simulate the actual path of the baseball. So my x is v sub 0 cosine theta of t. What should I write? 150 times cosine of 18 times t. T is time again. And then for y, we have negative 16 t squared plus 150 times sine of 18 t plus 3. So the first thing I'm going to do is we're going to just use the trace function. And now keep in mind, last time I had xbt, but this time t is not showing up on the graph. T is just the time. X is how far the ball is going this way. So I have to check 400 feet away. So I'm going to need to make my x max at least 400 to see what I need to see. Also, you're going to want to make sure you're in degree mode, because now I'm taking the cosine of an angle in degrees and the sine of an angle in degrees. Alrighty. Are you guys ready for window? Okay. So this would be 5 seconds. Probably that's enough if you think of how long the baseball would be in the air. But let's go to my x now. X represents the ball's motion going this way. And so I need to see 400 feet away, so I'm going to actually make my x max 425. I'm not quite sure how high the ball is going because it's only leaving at an 18-degree angle. That's not incredibly high, so I think I'm probably safe with 100. Okay, so let's graph and see what happens. And then let's trace, and what we're looking for is how high is the ball at 400 feet away. So I'm going to trace. I'm paying attention to X right now. So right now the ball is 185, 200. Okay. At 399 feet away, how high is the ball? 7 feet above the ground. Is it going to clear a 20-foot wall then? No. Now, you can't, because when you trace, if you tried to type in 400, it would do time. You can't, you have to just get as close as you can. Here, I'm too far. But 399 is obviously even before 400, and the ball's too low, right? So I'm going to write, so I have an explanation. At 399 feet away, the ball is 7.3 feet high. It won't clear a 20-foot fence. Okay. Now, something cool that you can do with parametric mode is, if you want, you can even draw the fence on the screen. Because this picture is a picture of the ball. Okay, this is a picture of the ball. So there's a way to draw the fence. And I'll give you the equations for that. Just so you understand, you don't need to draw the fence on there. We figured out with tracing what it was, but it's kind of something cool you can do that you can't do with regular mode. So to put the fence on, so these were my X1, Y1, right? In my X2, I would put where the fence is going to be. So how far is the fence away? 400. So we just put a 400 there. And then what we do for Y2 is we want to know how high it is, but we need to make it stop when T stops. So how high is the fence? 20. And so what I do then is I do T divided by whatever your T max is. Because then what will happen is once it gets to its T max, it's got, like, let's say it's 5, it gets 5 over 5, then it's 20 times 1 and it stops. Okay? So, would you look a second, do you guys have T max as 5? Okay, does everybody have T max as 5? So here's what we're going to do now. Let's put the fence in. In X2, we're going to put 400. And then in Y2, I'm going to do 20. And then I'm going to do T divided by 5, because that's my T max. Here we go. Ah, there you can see the fence. And it clearly does not clear the fence. Alright, so